For a century, quantum mechanics has delivered the most precise, empirically successful mathematics in the history of science. Its predictive power is absolute. Yet that mathematical precision is paired with severe ontological instability. The core vocabulary of the field, wave-particle duality, superposition, entanglement, describes a reality that seems physically contradictory. These persistent paradoxes do not mean the universe is intrinsically irrational. They indicate that we suffer from a condition of conceptual nearsightedness. This graphic illustrates the core issue, viewing a deeply fluid reality through the rigid lens of classical conceptuality. Historically, physicists forced an intermediate state of matter into the blunt vocabulary of fully completed atomic objects. The central mystery of the quantum domain, therefore, is an error of ontological resolution. Quantum theory successfully mapped a physical terrain, but we simply lacked the proper categories to name what we found. Theoretical physicist Philip Lillian introduces a corrective framework to resolve this exact problem, called Atomic Continuum Ontology, or ACO. The traditional classical view assumes a flat universe, one built from the bottom up out of discrete, indivisible particles. This diagram contrasts the outdated classical pyramid with the ACO framework. ACO proposes a layered sequence. Here, discrete particles are removed from the foundation. Instead, they sit at the peak as achieved stabilizations, emerging from an underlying relational ground. To eliminate the need for magical thinking or infinite parallel universes, physics must permanently abandon the idea of primitive particles and rebuild the entire architecture of reality, constructing it layer by layer. Lillian's framework divides this architecture into three distinct layers: continuum ontology, atomic continuum ontology, and atomic ontology. Looking at this 3D visualization, we define the extreme boundaries. At the base is continuum ontology, or CO, a deep relational ground characterized by distributed, field-like coherence. At the top is atomic ontology, or AO, the stabilized regime where localized, countable matter exists. This transition is governed by a mathematical seed equation. C represents continuum relationality, and A represents atomic realization. The governing variable is chi, the closure parameter. As this sliding scale increases, the system transitions from a distributed field into a discrete object. By tracking this single closure parameter, the behavior of the entire quantum domain becomes mechanically deducible, requiring no classical assumptions. We test this math by applying it to the universe's baseline, the quantum vacuum. Contrasting the standard empty vacuum against the ACO model, we apply the equation. The closure parameter is near zero, yet continuum relationality remains active. This proves the vacuum is a highly structured ground, dense with relational pathways, even without finished atomic particles present. Because the vacuum exhibits intense structural complexity without discrete objects, the assumption that particles are foundational building blocks of the universe is mathematically false. If we advance the closure parameter slider into the intermediate band between 0 and 1, we enter the true quantum domain. This middle layer is the regime of partial closure. It is an environment where continuum fields and atomic reality lawfully coexist in structured openness. This graphic details how partial closure automatically resolves the paradox of superposition. Superposition is not a particle in multiple contradictory states. It is partial closure multiplicity, a condition where several constrained realization pathways simply remain open and admissible within a single system. The many worlds interpretation attempted to solve this by suggesting every pathway branches into a literal parallel universe. ACO keeps the multiplicity, but restricts it to open structural possibilities within our single partially closed regime. We can apply this same logic to entanglement, entirely dismissing the need for spooky action at a distance. Entanglement is simply relational persistence. It is incomplete atomic separation. The interaction only appears paradoxical if you falsely assume the two correlated nodes are already fully independent particles. These phenomena are not metaphysical anomalies breaking physical law. They are the expected natural behaviors of an unfinalized relational structure. This leaves the final, notorious quantum paradox, the magical collapse of the wave function upon measurement. Legacy models define measurement as an inexplicable leap, a moment where reality suddenly solidifies out of pure ambiguity because an observer looked. ACO replaces mystical collapse with closure deepening across 4 stages. Interaction with a measurement device forces the closure parameter to increase. The system undergoes closure selection, isolating one pathway. Measurement concludes at AO stabilization, triggering exactly when the parameter breaches a strict mathematical threshold. The moment the threshold is crossed, the open pathway localizes. It becomes the discrete, countable detector click we mistakenly call a fundamental particle. Measurement doesn't require an observer to conjure reality. It is a strictly physical, lawful process driving an open structure across a mathematical threshold into stabilization. If we accept this new ontology, does it mean we have to discard the mathematical triumph of quantum field theory? Not at all. This diagram shows how ACO finally provides the correct ontological map for the mathematics QFT has been utilizing all along. QFT acts as the effective formal grammar for the regime of partial closure. Its operators, fields, and amplitudes perfectly track the distributed continuum relationality, while its scattering outcomes and quantized excitations track the final atomic realization. QFT provided the perfect mathematical syntax to track the intermediate regime. ACO simply provides the definitions required to understand what that math is actually describing. When we step back and view this theoretical architecture as a whole, the magnitude of the correction becomes clear. Discreteness and localized particlehood are undeniably real phenomena, but they are derivative outcomes, snapping into existence only when fluid relations are forced to stabilize. This model absorbs the valid observations of both the Copenhagen and many worlds interpretations, but discards their shared fatal flaw, the attempt to force a partially closed system into rigid, absolute extremes. This final graphic tracks the true trajectory of physics over the last century. Quantum theory did not discover a reality that was intrinsically irrational or beyond human logic. We simply discovered a profoundly structured intermediate layer of the universe that our classical languages could not describe. By recognizing the regime of partial closure, we restore rigorous coherence to physics, successfully bridging the vast conceptual gap between the continuous field and the stabilized particle.